Okay, so nice to meet you all. Okay, we'll keep making this session in English, even though everybody here is speaking in Latvian, because I will also publish this later. So, anyways, in the chat, please get the template. Also, the template is inside the Google Classroom. And just in a second, I will share the screen. Today, we're going to work on another deep metric learning model, very popular. So this is a little bit different from the ones that we used before with the contrastive loss. So for the basis of this work, we're going to use the FaceNet publication from Google 2015. I also dropped that in the chat. We'll be sharing the screen just in a moment. And then we'll look over some of the features of the. So basically, what I'm trying to do today is that, as in the team of the researchers and the commercial projects that we're going to run after this course, is that we often need to implement papers just based on the documentation from the publication, so just from the equations. So we'll try to do that also today. So we'll try to adopt our template for this particular publication. And if you have any questions, type in the chat. I'll try not to make this too long, but hopefully you will understand how it works. So let me share the screen. Again, the idea is kind of the similar, like the same, basically, as with other deep metric learning models. So let me first, I will share the Safari screen here. Okay, so here we have the encoder, right? We have the Z latent vector, and we have the input images and the loss function. So the input images, in this case, they are faces. They can be any biometric data, or also can be any kind of pattern-related data that can be measured with regards to their similarity. So, for example, if instead of these images, you will have some operation of the sensor readings from, for example, some factory, and there are, for example, these two are normal operation. This is some anomaly operation, so some problem. Anyway, or some deviation, or even better, if you can measure the deviation between those two. If you have some scalar value of temperature or some output of production or something, like how different are those, so that would be even better. So you say that you didn't understand the sample mining in the chat. So okay, we'll look at the sample mining also with regards to the triplet laws, because triplet laws also have the sample mining in their paper, and but the kind of the worst pairs of samples, that's something that you should be able to kind of understand. It will try to help you out. So the idea is that we have the same model. So we run the same model 3 times. In this case, there are some versions where you can run it n times, and then you have not triplet loss, but n tuple loss or something. And the idea, what you want to get out of it, is to have the positive pairs closer together in the embedding space, high dimensional, of course. Like it can be like the hundreds of dimensions. You want these to be together and separate ones to be farther away. And also, if you think about so what is the worst samples, what are the best samples? So this, I think, image is from, just a second, from the FaceNet paper as well. We'll try to explain that. Hopefully you will get it. And here, like, so what you see here is that the anchor point and the negative sample. So, and after the learning, the negative sample and the anchor point have larger distance, and the positive and anchor point have smaller distance. So in this case, let's see. So if we have a situation where we would have multiple positive points, right? And the multiple negative points. So we need to choose from the positive points and from the negative points. So we'll try to answer the question in regards to the question in the chat. So thank you for asking questions in the chat. It helps me to understand what you get and what not, and how can I explain something more. So, okay, let's see. So you have the red ones here, so the negative ones. So let's see. These will be, for example, 1. This will be identifier 2, and this will be identifier 3, right? So with regards to the anchor point, what do you think, which one is the worst sample? So with regards to anchor, which is worst? So worst in a performance type of way, and basically it would be the best for the training purposes, but the worst in the training type of, I mean in the performance, you know. So we have one, Christopher saying the first one. What about others? Yeah, so I think you get it, right? So that is the worst one. And this is the reason of the sampling, right? When you have the mining, I mean, you have the mining operation and you have some choices. So we can run all of the combinations, or we can choose just the worst ones. So this will be the worst pair for the negative ones. And for the positive ones, this will be like the ball that's already there. And to do this programmatically, of course, then you need to do the sorting, right? Or maybe you can also do it a faster way if you just try to find the smallest distance or the largest distance, you know, just one loop. So that's the complexity of n. That's much better than doing the full sorting. But if you do full sorting, that's also could be beneficial, because then you could do like some kind of weighted the mining, you know. But in this case, don't make it too complicated. You can just make one loop and try to find which one is the closest and which one is the farther away. So that's the idea here. Okay. Hopefully you understand this part. Okay, I guess I need to remind also the idea of the margin. We'll try to find some images. Okay, so I think I did not share this image before, maybe this one. And so I like just to find some new images for these problems, because I guess the more of these you see, kind of the better hopefully is the understanding. Okay, let's see. So this is something that I found just from the internet. But basically, so we have the hard samples, the semi-hard and easy samples. So that's one way of classifying it. Let's see, there is actually triplet loss here. There is another type of loss, DMHSL. I guess this is something like a maybe histogram type of loss. There are, actually I will publish soon one paper and some like a chart of all of the triplet loss functions that exist at all. Like there are like so many, like I think over 30 variants. So it's really not easy to now say exactly which one was it. But here the idea is following. So we have the N, so the anchor is A, right? So what we want is that all of the triangles N. Okay, I see some other question. I will check it in a second. So we see the anchor and we see the negative samples. So what we want to do is to push all of the negative samples out of this radius alpha, the margin. So the idea is that we want to make the situation that the positive ones are inside the, the positive ones are inside the margin, and the negative ones are outside the margin, with the idea that basically so that these kind of clusters would float in the embedding space and align themselves in a way that they would represent the underlying data structure. For example, the people with long hair would be more in the one side of the spectrum, and then with the short hair another side. Then for example, I don't know, like people with the hats in some part, with the glasses in another part, and that all would happen automatically. And we try to do that by not enforcing very strict like clusters, but just saying that you cannot have that sample in that alpha range. So that's one way how to do that. There's, if you look at these images, interclass, so anyways, yeah, you need to think about a little bit more about the bottom image, but this one, it's kind of clear. And so that's one. And then the semi-hard area, I guess, is the further away point of the positive ones. And if you like subtract that one from the alpha, you would get that yellow area there. So that's like the distance between between the outer edge of the positive cluster and the edge of the like this boundary between the classes. Anyway, so but we will try to code it, and then hopefully it will make sense. So with the hard and semi-hard mining, programmatically you check if the sample matches the hard constraint. If it doesn't, you check if it matches semi-hard constraint, or you check both and sample either way. So for the tutorial that we did last time, and also I think the this one for the FaceNet, they use both. But you can use also either. So it's not something that is always definitely need to be used, but at the same time, the way how the triplet loss function is formulated here, it's not really that. So to make it work kind of more stable, it would be necessary to use those constraints. And already, if you try to implement it, you understand that if you apply those constraints, there's high probability that very soon you would not be able to train at all anything, because like a lot of samples would not fall in that constraint at all. So that is a problem, and there are some solutions for that as well, but we'll go step by step. So, okay, this is what I think this is one of the constraints here. We had the two constraints that we discussed last time. Let me check semi. I think actually, yeah. So this paper was the one who proposed the semi-hard and hard. So the semi-hard constraint and the hard constraint, and the loss function itself looks like that. So if you think about the loss function, this one is different than the contrastive loss in some ways. So first of all, contrastive loss did not require always to have the pairs with regards to same anchor point. Here we have the same anchor point here and here. And there is the positive and the negative distances, plus the way how it's written. So it's written that the positive minus the negative pair plus alpha, and all of this is maxed by 0. So if you think about what's the shape of that function, it is quite different from the contrastive loss, and kind of like in some cases like it basically it works, but in general, like it's there are some updates to that is a little bit better. But let's go step by step. So we'll try to implement this one, and we'll see how we need to change a little bit formulation. And also, you see there is an L2 norm at the end. Let me check if in my template, did I have L2 norm at the end? Yeah, we have. Okay, that's great. So that means that most likely this is a Euclidean space. If that would be cosine space, then L2 norm would not help much. Okay. What else do we have here? I think the main advantage of this one was that those constraints and applying to that triplet loss. Here, the architecture, if you look at the architecture, we will probably not change much the architecture. But, okay, this one was not, I was thinking that this was with the max out functions. Let me check, was it? Oh yeah, there is a max out. So there are, like, I guess, multiple versions. So NN1 use max out functions. That's kind of interesting. So I think we have not yet covered the max out, but this is kind of interesting hack for. So I'll try to find some reference with regards to max out, and we could add actually max out also to our model. So the max out function itself, by the way, is kind of like a function approximator. And that is a little bit dangerous, because if you start adding function approximator to already existing very powerful function approximator that is neural network, then you could get really not good results. So I will try to give you some visuals of the max out, and basically it's quite easy to understand. So if you have multiple linear layers, the fully connected layers, you could have, for the same input features X, you could have multiple linear layers, and if you chain them together, not chain them, but if you just pick the maximum value out of all of these linear transformations, and you could also do that for every dimension even, like, and if you get the max out of that, you could easily think of that function where you have multiple linear layers followed by the maximum as something that can describe almost any function. So if you think, we can maybe add some other image. So you know the leaky ReLU, you know the ReLU, 10H, all sorts of. So if you have a max out, you can have, for example, two linear kind of projections. So for example, this one and this one. So if you have this projection and this projection, or maybe this projection and this projection, and then depending on the X, you would activate even either this projection or this projection. Depending on the X, maybe you can activate this one, this one, this one. So this even looks something like a L2 shape, right? You can have L2 shapes like sigmoids, all sorts of things. So just by putting together max with many linear layers, you can simulate any other function. So that's quite cool, actually. And the way how normally you would add the max out layer is that you would have, instead of one fully connected layer at the end, so you will have a lot of fully connected layers, and then you will have max out. Probably usually you just use two, I guess, max out layer, two of those fully connected. And then basically that would be your last function there. In this case, they use multiple of those and even multiple fully connected layers. So this is a bit tricky. So I don't think that adds much value there. As from my experience, the more max outs you add, the more unstable everything becomes. Like it's as I say, it itself, it's kind of like this approximator, and the model itself is also approximated. So anyways, this was 2015. So right now, people are probably not using that as much. Anyways, let's go back to the code. So I will share my screen for the code. And we'll make some changes in the code. And I will drop those also in the Jamboard. Where is my code? I think this one. Okay, so I'm not sure like how much did I drop from the original version. So here I made a new function, reshuffle, and we will also change a little bit in the dataset get item. So for the triplet loss, the first thing we'll start changing the dataset itself. So we want dataset to produce data in the way that will be nicely processable with the triplet loss. So one way how to do this would be to produce triplets in beforehand, and that's why I have a reshuffle basically. So the idea is that after every epoch, I want to reshuffle triplets, because triplets itself, like I don't want to have that model learns specifically that those pairs with each other should matter. I just want that the model learns the generic features that should matter, not that the exact pair matters. So that's one. And let me quickly find a little bit my notes. But I don't have everything in my notes, so anyways, I will need to do that. So first of all, what I did here is I selected by the class indexes. So we have 10 classes here. We already know how many classes we'll have in the training set. And I added that for each of the class indexes, I have a separate list of all of the indexes in dataset, because I don't know exactly if the dataset is ordered or not. And that will be safer way. And then here for the reshuffle, I want to add samples to the sample to this sample list. And the way how we'll do this is by using the while loop probably. So here we can have while loop, and in that while loop, we'll have is triplet found. False, and if if it is not found, the triplet is not found, then we'll break out. Or we could probably, I guess this is not nice. Let's make it different. So first there will be triplet found true. So you know that definitely first one should be there. If there is even not one triplet, then this is really bad. So that will be like that. And let's add here, so there will be false. And then if it's found, then we will add it. So, okay, so that's the first part. Then the other one, we want evenly add the anchor points. So for the anchor points, let's see. So the anchor class, we could add a class. So this will be a class, will be anchor class. So in range of 10, so we'll go over each of the classes that we have multiple times, many times. So if len, so here let's see. Just also want to make it a little bit more generic. Let me think how we could do this. Okay, let's not make it too difficult. There is one thing missing here, that but let's not make it too difficult now. So here we'll have, let's make it baby steps. So the first one will be then the a class. So we'll check if we have at least two same class samples. So if we have at least two same class samples with regards to anchor class, that's good way to go. So then the next one would be the index for that sample that we want to pick, random choice from the class indexes a class. Okay, so we have one choice of this. Of course, we need to remove it because we don't want to include that point again in the dataset. IDX. So we have this one. Then we also need to have another choice here. That will be then the positive index. We have the anchor index and we need also the positive index. So we need three samples, one with a positive pair and one with a negative pair. So this will be then the positive pair. And then for the negative pair, we need to look inside the other classes. So let's see. So these will be, for example, other classes, all classes. And here we'll add with the for loop, so all class in range of 10. By the way, of course, this code can be written a little bit more efficient, but trying to make it so that it's understandable. So all class with the A class, where it's not matching, so the negative pair. And also, so if length, so if there is at least one sample available here in the all class, then that's good to go. And that means that we can add the candidates, so the candidates of all class. So we are adding the candidates for the negative ones. Again, here there is a potential already for mining, but again, this depends. Like you can have mining in multiple places. Like so, if we add mining here, that would mean that first of all, like this would happen in between epochs, and during the training, maybe something already changed. So we could add also mining as we did last time in the middle of the training. That might be even more beneficial. So here, if len of all classes, so if there is any negative candidates available, then we can continue. If there are no negative elements available, then we should not continue. So then let's see, negative index from random choice of class indexes of, I forgot to just, oh, no, yeah. No, I need to first also get the negative class itself. So n class should be something random choice from the candidates that we have. So all class candidates, other class candidates, all means other. So from those, we pick one candidate, then we pick one IMDX sample from those. By the way, the class indexes, again, I'm just saying that it's a list of each of the classes, and each of the classes have sublist with all of the indexes in the dataset. So that's why it's an index. So negative indexes here. So then we also want to remove that negative index from n class here. So that's great. So we have 3 indexes ready. That's great. If we have 3 indexes ready, then we can add those indexes to the self samples append, and we can use the tuple here like that. So there could be anchor index, positive index, and negative index. By the way, for the mining operation, it would be great to have at least 2 positives and at least 2 negatives. So that would be excellent. Then we can choose between, with regards to anchor, which one of those 2 positives are best ones, like, I mean, the worst ones in the performance and the best ones for the training, and for the negative as well. If you would have for each of the A's 2 P's and 2 N's, that would be better than this case. That's why I was a little bit hesitant to move forward. but let's keep it simple. So right now we have just once. So then is found, is triplet found is true here. So we added one. And that's a bit about it for the reshuffling. So I will drop that in Jamboard. Hopefully there is no bugs. I didn't test it yet. So drop this from line 56 onwards. So this will be the reshuffling procedure. I think I also forgot to add reshuffling procedure to after every epoch. That should be done. So if we go a little bit scroll down, so I added that to the Jamboard, by the way. So if I scroll down a little bit. So first of all, reshuffling is important only for the training dataset, most likely, or actually it would be important for both. On the other hand, yeah, so anyways, for the evaluation of the accuracy, we will not use the triplets. That's another point. So let's see. So that's why it would be important for training only. For evaluation, we will use the full data set. And of course, the test data set is something that we want to use primarily for evaluation. But of course, if we also collect test loss, then maybe that would be beneficial. So anyways, I guess the test accuracy and the test distances of positives and negatives would be more important than test loss in this case. So the data loader, okay, data loader, that's we have. Then dot data set reshuffle. So we can reshuffle for both anyways. So let me see. Yes, this is the same. So this should work hopefully. So after every epoch, we can reshuffle here. Hopefully that works. I will add this also a little bit later in the Jamboard as soon as we will code some other part. So if I go up here, we have now the get by item. This will not work at all because we have data here and here is the samples. So what we should do is copy this one because we still need this one, by the way. So because we also want to go by the whole data set one by one to evaluate the accuracies and everything. And for those parts, maybe that's easier, just go one by one and not to go by triplets. So here we can have, maybe let's call it this one as get single item, like that. And for this other part, we will change it slightly. So this will not be a big change. It could be quite easily like added. So here, what we want to do is to have A, IDX, P, IDX, and N, IDX expanded from self samples by IDX. So that we expand the tuple in those three variables. And then we will return very complex tuple. So we'll have tuple that consists of basically three sub-tuples. And the good news is that the batching procedure can deal with this as long as all of the dimensions of all of the tuples or lists are the same. If we would have the situation like in the time series where each series is different size, then we should add padding. Otherwise, this would not work. So here we can have the get single item of the A index. So this will produce the pair of X and Y for the anchor. Then the pair for the positive. And finally, pair for the negative. So hopefully that's fine. So I will drop this also to the Jamboard. So we have three pairs there. I mean, yeah, three pairs of the input variables, but those are not the pairs necessary for the triplet loss itself. Remember that for the triplet loss itself, there is distance of the those with the anchor point. You know, like it's not the, so here we have the Y's. The Y's are basically needed for just for the evaluation purposes, for the testing and debugging. If we are honest, actually, we could leave out Y's because we have this procedure for the later, but just to make it clear, we can we leave them in, but it's not necessary actually to have the Y's here. Maybe we should remove them here as well. Let me think. Maybe we should remove them. Okay, let's remove them. I don't like them because they are not needed here. They are not needed here. So the hacky way to remove them probably would be just to use like 0 like that. Okay. So that would just take the X and leave out Y. The proper way would be not to actually transfer Y to the long tensor at all, but let's stick it in this way. So I just don't want to make it too long and too many copies of the same code. Yeah, as I say, for the accuracy measurements where we need a Y, because we need to know what was the ground truth of the class so we can measure the accuracy, right? So in that case, we will use just this get single item function and the length of the data. But for the training procedure, we will use this one. Okay, so we have this one in the Jamboard as well. So I will go scroll down, and we need just to change the last part of here. It's that we will produce out of the data loader now, not what we had before, but AX, PX, so the anchor X, positive X, and negative X. So we have those three, that's great. Then the last thing that we need is to calculate, okay, first we need to actually pass through the model. Again, so the best way, maybe I will add that as a homework. I will try to not make the homework too difficult. So to do here would be to concat and pass once. So just to illustrate a little bit better, I will pass it 3 times, but the best way would be just to pass it once, not 3 times. So here there will be Z, I mean AZ, so the anchor for anchor Z vector, and anchor and positive X and negative X. And here, if we think about it, it's also quite cool because here these 3 functions we call here, it means just basically the way how PyTorch works. For example, if you have GPU that cannot hold all of the concatenated batch together, so it's not big enough, you know, like you don't have 16 gigabytes of GPU RAM. So maybe that's good that you can pass it 3 times. So every time when you pass it, like the gradients are like, so the gradients will be accumulated anyway later. It depends, like it could be possible that it maybe the accumulation of those gradient of that forward pass during the graph can also require extra GPU, but hopefully not too much. So anyways, that's one way to do this if you cannot pass it once. Like usually you would do this like forward and then backward. Okay, sorry, I think it should work like that. So if you don't have enough space in GPU, you can kind of simulate batch size by calling it multiple times. That's the same thing that happens with the recurrent neural networks, because you're repeating the same cell many times, and the backpropagation through time accumulates the gradient anyway. So that's cool. Anyway, so let's write the loss function. So then the loss function is the torch mean. So the mean is just the same as the sum, but with the kind of scaled feature. So then there will be the torch rel. I guess the rel is just this most simplest way. You can also write it as a maximum, and then the torch zero is like the input, and that would be also the same thing. But here we can use it in this way. So this basically is the max x0. So that's what we have here. And then let's call the torch. And by the way, do we have f here? F, no. Okay, let's add f because sorry I forgot it. So usually you would call this torch and then functional as f. Let's see if I use it somewhere. Yeah, I used it already. So as f, that's kind of common way how many times in PyTorch you can see in many libraries that they use it in this way. This is like the same way as for the plots, for the pandas, for the numpys. There's like this non-written rule that for the PyTorch, usually for the functional module, you write this large F. I don't know, somebody started it. So here, okay, let's see. And functional, this is cool. So sorry for scrolling. So here I added also to the Jamboard this small notation. So f phase distance between the AZ and the PZ, right? So that's the first phase distance. By default, that's Euclidean, right? And if we look at the equation, so we should minus that one from the negative one. Then we should add plus margin. So, and that's, I guess, about it. Except it will not probably work fully because in the next part we need to change also the way how it calculates accuracy. So I'll try to run it, see if it works so far, and if it works, then I'll add it to the Jamboard. Okay, choice, random choice problem. Could PCA working? So please elaborate on that. What do you mean by could PCA whitening help on that? Exactly which part would it help? So PCA whitening helps in a lot of things, but not sure about exactly what you mean. So all classes, there are, there is a bug here. Okay, that's so easy to make these kind of bugs, sorry for that. So here, of course, the random choice should be from the O classes, not from the O class itself. So we're trying to get the N class from O classes. So I will fix this and add this to the Jamboard. For that PCA whitening question, if you can explain a little bit more, what do you mean, which problem would it solve, that would be great. So I guess hopefully this far it will work. If this will work, I will also add these lines of the forward pass to the Jamboard. As you see, the loss function is kind of interesting and really simple. Here, of course, the mining procedure is missing and the constraints are missing. But that already you know how to do. you use just somewhere to use PCA, right? You could definitely use. By the way, the fun thing is that I think from the you can do the at least the linear PCA and even also the kernel PCA. That's something that can also be backpropped through. So you could even add the PCA as part of your model. That would be interesting research. I have seen some occasions where people are trying to use it, but not probably for the deep metric learning. So that would be really fun to do some research on that direction as well. Maybe hopefully we'll get some cool results. So okay, it worked so far. So I will add this part to the Jamboard, and then we need to change a little bit the last part of the code so the accuracy and those things should be calculated correctly. Because now, if we just call from the data loader, it would give us something bad. It would get, like not bad, but it would give us just those 3 instead of 1. So just to make that it would work as before, so let's see, data loader, data set, and if we want to have here, so let's say X and Y, like if you want to work with X and Y here, by the way, already that's already to the Y, so need to change a little bit. So here will be data, and we could go by length probably, and this will be IDX, just IDX of data. And then if we would call the data set XY of get, okay, this would be really inefficient way, sorry. It would work. The first thing, it would work, but it would not be efficient. Just a second. We'll think about a second. I think we can make it, we can make kind of rudimentary batcher here. So get item ID X like that. So it would work, but it would pass every sample one by one, not by batch. That would not be probably great. Let's see. We should accumulate a little bit batches. One is of course we could change the behavior of the dataset or create another class of the dataset. Maybe that's a good way now here to explore other ways. We could go by batch size up. Okay, let's do that. So in range of from 0 till dataset by batch size. So 0, comma, this, comma, batch size. That would be fine. And then here we'll select these ones. And I guess we just need to have another group here, unfortunately. So there will be the Y as a list here, and X as a list and Y as a list. Then we'll have a loop for IDX in range of IDX data, IDX data plus batch size. And there is a possibility that it would not go till the end. So we have X and Y, fine. These can be items. So just IP item. And here we also need to check the upper bound. So if IDX is lower than this one, then we produce those and add append to IDX. So definitely this code should be extracted in some kind of class. So we should not do this like twice, because below we need to do this again another time. But just to not make it too long today, so we'll use it in this way. Stack wise, and we also need to stack X's. Okay, it should work. I will try. I add the breakpoint here. And unfortunately, I will need to copy this block of code again for the bottom part, but at least it works. So of course you can imagine you can make it in a different way, more efficient. But just in case, like, so the idea is that you want to make your data set so that it always produces the triplets, or like a triplet with extra pairs, so you can choose which one is from the two, which one is harder, and then include that one. And for the calculation of the accuracies, you should not use the formulation of the triplets, but just use everything. So of course, probably we could use triplets in the sense that then we can select them out of those. Okay, there is a problem here. The code works, but the problem is that now I included data here, and now it will just pass through the whole data set. And before I had this testing of the max length. So should use index now IDX data. Yes, thank you. That is a bug here. Yes, that is a bug here. Thank you. So I'll drop that part of the code as well in the Jamboard. And for the next part, it just need to be copied again. And of course, right now this doesn't produce what I want. So because here, if you look, we have the max length, right? So the max length is something that I use for the debugging purposes, so I don't need to run the whole data set. Maybe I could kind of hack it in the bottom part as well. So you could use something that you should never use, some kind of spaghetti code here. You just don't want to make it too long. So if this one is 0, or what was it? Sorry. Yeah, 0. So if this is 0, then we will do that. If not, then we'll do this. So added spaghetti here. Okay, but the line, so there is a bug here. I need to change it like that. So I would not be happy with this kind of spaghetti. So let's say here we'll have the max size, max one, this one, and also here. So I added this just to make sure that my code works a little bit faster, so I can check it. Again, I'm checking everything on CPU. If you have GPU, then you need to add those exclusions also on top. But again, so here, the way how to calculate accuracy using the clusters, using the sensors of the mass, using the radiuses. By the way, I'm not sure if we covered the radiuses, but you can imagine if you can calculate which one is from the center of the mass, the further away point of the positive class, you can draw a radius and then calculate how many samples fall in that radius. So that is another method. So there are multiple methods how to calculate accuracy. Also, you can add the PCA whitening for the Euclidean, and that part is not changing. The only part is changing the loss function and the sampling methods and the mining methods. So not sure what's happening. It's working somewhere. I guess it's working very slow for my computer. Anyway, I will try to maybe make it smaller, not the length of 20, but max length of 20. Okay, yeah, 20, and the batch size 18, so that will be interesting. Let's see. If it will work, I will add that part also to the Jamboard. And next time we will look at additional extension for the triplet loss. So there are a lot of like triplet loss extensions. I just want to look at one that I think is very promising. So I think maybe 2 years ago that there was a published version of the way that there's learnable kind of center of the mass for each of the class. So we will look at these kinds of models. So I forgot the exact name of that loss function, unfortunately, because there are so many of them. But we will look at very interesting type of triplet loss. And after that one, the remaining sessions that we have, we will also look at the GANs, so generative adversarial networks, where that can also be used for the deep metric learning, by the way. And we will look first of all at simple GANs, and then we'll look at some ways how to encode the kind of encode the z vector without knowing the distribution. So that will be interesting. Okay, I'm not sure really why it's so slow for me right now. I really hope that this part of the code works. Just like it's incredibly slow right now. So, okay, I guess probably because I call it 3 times for every of those samples, so it just takes a lot longer. Anyway, so I will add this part also below here. So we need twice the same code. Again, as I say, better to use some kind of function there or class. And I added already that to the Jamboard. So you need it twice. Okay, I'll try not to run it with the plugin, but just directly with the run. Okay, so I don't want to take too much time of yours today. So I hope that's today, like the things that we covered, like it's, as you see, it's not too difficult. At the same time, it requires the understanding of the structure, how it works. For the homework, I will just add that you could concat and pass this once. I also want to add that you would have for every sample 2 samples, so there would be 2 positives and 2 negatives, and you would choose the worst one from like the one that you should use with the positive ones. So you would compare one anchor with one positive, one anchor with other positive, one anchor with one negative, and one anchor with other negative. So you do that comparison using the pairwise distances, and then choose the closest one and further away one, and pass to the loss function, and that's it. So that would be a good extension. So if you would like to fully make it as it was in the triplet loss paper, then you would also need to have those constraints. But again, that's not hard to do. But I don't require actually to put the constraints. So so the comments on homework 7.3 with regards to mining, of course, I will check that, and definitely probably like for the Christopher's, like there are some people who are doing the thesis and the final work. So definitely after the final works, we will have even more time of exploring this. But my other course in university ends next week. So the next week I definitely will have time to go over all the homeworks in this course. So just wait a little bit. If you have some questions and you're stuck somewhere, please write in the WhatsApp or email, and we'll arrange meeting and help you out. So hopefully this is interesting. Again, new model today. Next week we'll have another variation of the triplet loss, and then we'll start working with the GANs. So as you know, all of these models are quite powerful. You can, like, the imagination is the only limit what you can use with them. So hopefully that was interesting and didn't take too much time. The homework hopefully will also not be too difficult, and we'll meet next week. Okay, bye bye. Yeah, next week. By the way, next week there is a thank you. There is a holiday next week, right? We'll need to schedule the meeting on Wednesday, most likely. So sorry for the rescheduling. If somebody cannot make it, I will send the video. add the video in the Jamboard in the classroom. So thank you, really thank you for reminding me that. But still, there is a quite interesting material ahead of us. So hopefully you can follow up on this. Okay, so bye-bye.